A very good evening to Dr. Leela, my examiner, and Dr. Noor Shikin, my supervisor. For this proposal defense, I'm going to talk about my classification of EEG for imagery motor function using 3D convolutional neural networks, or 3D CCN in short. So for my presentation outline, I'll be talking about the introduction, the problem statement, objectives, scope of work, theory, literature review, methodology, grand chart, conclusion, and references. So as a brief introduction to my topic, a brain-computer interface is a computer-based system that acquires brain signals, analyzes them, translates them into commands. Now, one of the main uses for BCI is motor imagery, which has countless potentials from the control of prosthetic limbs to cybertronics like Robocop here. The choice of brain modality that we have chosen for this motor imagery experiment is EEG. Now, why EEG? It's because of its high temporal resolution. That means it's able to detect changes in the brainwaves very quickly. It measures brainwaves directly, as well. The level of expertise needed for it is fairly low compared to the others. So, some of the problem statements that I face are EEG signals are non-linear and non-stationary in nature, meaning it's very difficult to decipher useful information from it using normal conventional statistical and frequency domain methods, right? And also, traditional feature extraction measures such as fast Fourier transform have low spatial resolution and high spectral leakage. Traditional machine learning methods such as SVM are not flexible. They're feature vectors, meaning that they can only uh, get specific features, okay, that are given to them. And also, we are in search for a low error classification method that is, nearly 100% classification accuracy. Therefore, my objective is to develop an EEG classification algorithm based on 3D CCN for 6 motor functions, okay, and also to analyze and test this algorithm for its functionality, consistency, and accuracy. So my scope of work can be broken down into 3 parts, okay. The first part with being EEG data analysis for left and right motor imagery, and then we move on to MATLAB where we process this extracted data, and then lastly, once we've got all the features extracted, we can classify it using 3D CCN techniques, probably in GoogleNet or the NextNet. So for the theoretical half, as you can see, this is the human brain waves, and it's broken down to 5 parts, which are gamma, beta, alpha, theta, and delta. So from what we learned is the frequency band for linked with motor imagery are both the beta band and the alpha band. Okay, and over here we have the electrodes that we are planning to use. Okay, these specific electrodes are related to motor imagery function, especially these three, which are C3, CZ, and C4, which are important for our uh, experiment. So another important piece of theory is the classification methods. We have deep learning and traditional machine learning. Now, the two volunteers for this are CCN for deep learning, and traditional machine learning we have support vector machines now. Now, why we chosen CCN is because CCN relies on layers of artificial neural networks to generate its feature vector, while support vector machine relies on hand structured data to identify its feature vector, meaning that it would require the user to feed information to it with freehand. Also, 3D CCN is more effective for non-stationary data such as this EEG signal, so that's why we've gone with that. So these are some of the literature review that I've gone through to understand my experiment better. Okay, so one of them is EEG datasets for motor imagery and brain-computer interface. So this is where I've collected data for my specific experiment for left and right motor imagery function. Okay, next we have an analysis of effects of EEG and frequency band classification. So this is where we learned that the 11 to 40 hertz range is where most of the motor imagery function happens, as well as the specific electrodes used, the main electrodes used, which are C3 and C4 for motor imagery functions. Next we have methods of a signal feature extraction using these two methods, which are fast Fourier transform, AR, and wavelet transform. So from here we learn that wavelet transform is pretty effective, and we've chosen to go with that. Next we have EEG based emotion recognition. Okay, so this from here we learned that using 3D CCN. Okay, so here we learned that 3D CCN is pretty effective at classifying brain non-linear and non-stationary brain functions. Okay, and lastly we have a comparison between support vector machines and 3D CCN. So from here we learned that 3D CCN is quite effective compared to support vector machines. So that's why we've chosen to go with that. Okay, so this is a summarized version of the methodology. First, we have the EEG signal itself, then it goes through a bandpass filter, followed by normalization, then it goes through CSP to determine its feature extraction, and then we have another wavelet transform to further enhance that. And lastly, we go to 3D CCN where we classify it. So this is one of the pre-processing that I've already done for patient S29. This is his EEG data for his first electrode 1. Okay, so what happens here is the data is extracted from the data set and converted to a matrix structure. Okay, next it's passed through a bandpass filter depending whether you want A, alpha or beta. So here I put alpha, and then we get this EEG signal, and lastly we normalize this signal so that it can fit into it will be easier for it to be class what do you call feature extraction later. Okay, so next is bot for feature extraction. Okay, now there's two feature extraction methods. One of them is CSP, which stands for common spatial pattern, and one more is wavelet transform. Now this common spatial pattern is a filtering method where it sends the EG data into a new space where it's divided by its one class by its maximized variance and one more by its minimized variance. Here maximized, here's minimized. Okay, and then their data will be sent into a wavelet transform where it is split into again two by one by high pass filter and one by a low pass filter. So the high pass data filter data gets capped while the low pass filter data gets again sent into another two splitting bins where one is capped and one is again split again. So for example, here we have an EEG data where it is splitting the bands, okay, from data to omega. So the high pass filters out all the high data while only the low data is left. Then again, that low pass filter allows the high data to continue going, where again it is high pass one is split out and kept, and then the low pass is taken, and so on, so forth. And then this data, all this data are converted to a scaleogram and sent for classification by the 3D CCN. So now once it's converted into a scaleogram, which is like an image actually, so this 3D convolution is memang made for images lah. It's better on images. So the first layer we have is the convolution layer where it will turn that image, it will do convolution of the image and turn that into usable data, processable data, and it will learn from that parameters of that, and each kernel has different features. Okay, so multiple kernels are used in each analysis. Next we have the pooling layers or the subsampling layers where it does downsampling is done on the activation maps created during convolution. So basically what it does, it extracts further the features that are kind of similar within the previous convolution layer. Okay, and then lastly we have the fully connected FC layer, which is separated from those two. Okay, so once you have the data from here, it is transferred into this fully converted FC layer where it goes through an interconnection of nodes, somewhat like a fully converted neural network. Okay, and then it's assigned with a value called a logit actually, and it's actually the last step because it uses a lot of computing power. Okay, then once this data is done, it can be it's already classified into several forms. So this is the grand chart of my project. So first we had the project selection, followed by the problem statement, objective identification, followed by the literature review, collecting the data sets, the data set selection based on selected electrodes, and then the pre-processing of the selected data sets, which will be done by these 3 weeks, and then lastly the feature extraction using CPS and wavelet transfer. So in conclusion, I hope to be able to create a classification algorithm for motor imagery with high classification accuracy, and also develop a classification algorithm for 3CCN for 6 motor functions, and lastly to allow the algorithm to be applicable in any field of PCI, hopefully. So these are all the references that I went through to get my answers and decisions. And lastly, I would like to thank you for listening to my presentation. Thank you very much.